Hello everyone, this is Amr Muhammad and we are talking now about our traffic engineering class CE432, and now we are starting chapter 3 in this class, which is some kind of a repetitive talk about some of the factors that we use in traffic engineering and also in transportation engineering. Therefore, since we have already talked about this before in the previous course, I'll go a little bit very fast in this because you might have heard this before. So let's go ahead, guys. We're going to talk about three things. We're going to talk about the road user. We're going to also talk about the vehicle, and also we're going to talk about the roadway. Vehicle and the roadway are being discussed together. So let's start, guys. So when we talk about the elements, and you might remember this slide in my classroom last year, when we talk about the different elements that interact as traffic stream and they cause all the issues that we talked about in the introduction. When I say issues, I'm talking about congestion, I'm talking about environmental problems, and definitely we're talking about safety. And here, that's the problem that we try to solve: congestion, safety. These are the four elements. Number one, we have the road users, the people. And the road users come in different shapes. So number one, we can have the drivers, we can have the pedestrians, we can have the passengers on the bus, we can have pedestrians that cross the road and share the road with the drivers and the cars. We can have cyclists, and cyclists also a huge thing, especially in summertime, and they share part of the road. We try to include them in our design. Highway designers do that, and also we as traffic engineers, sometimes we design our road to include everyone, including also cyclists. Sometimes we have cyclist signals, cyclist routes, and we do some traffic work for that as well. So this is the first main part and causes the main issues of safety, because while we deal with people, we're going to talk about this today, when we deal with people, we have some kind of inconsistency because we deal with different psychologies and different kinds of people. Then this will cause issues. And then finish now, talk about the people. We talk now about the other factors, which is number two, vehicles here. So vehicles are the second thing, any kinds of vehicles. When I say vehicles, vehicles include cars, they also include buses, and they include any other kind of vehicle that can carry people. Number three, we talk about streets and highways. We're not going to do much in street and highways in this class, because this class is mainly how to control traffic and how to help the designer to make use of the best out of the best of this, what we have here, streets and highways, to carry as much people as possible and to reduce the problems of safety and congestion. So we have here different kinds of roads. And then number four, which we'll be dealing a lot in this class, the control devices, anything that helps us control the road and control the people, give signals to the drivers, communicate with the drivers, is called control devices, starting from our beautiful traffic signal, which is a main part of a traffic engineering class, and also lots of markings and signs that gives lots of information, warnings to the drivers, and give the driver some legal information like speeds, also warns the driver, tells the driver what to do, and gives orders to the driver. These are called control devices, and we will be dealing a lot of these in this class. Also, not only these four things, there's another additional input, which is environmental conditions. Well, anything related to environmental, the environment, the weather, is discussed also as some kind of an input. It does not affect us much as the other four, because it might be temporary, it might be something that you cannot have control on, but you try sometimes to add your touch as a traffic engineer to help solve this problem. In other words, if you have lots of snow in the area, you can you always find these signs on the before bridges. Be careful, we can have ice, or when we have fog, sometimes we can add as traffic engineers some signs that tell us that we have fog. So we have rain, snow, fog. Other cities have dust storms and other environmental things that might have an input and cause problems for the drivers. Now let's talk about the first one here. So when I get back here, when I talk about the road users, this is the first one I'm going to talk about. And you might remember this talk in previous class. That's why I'm going to go as fast as I can to make it interesting, guys. So we talk here about road users. So we have a problem with dealing with people, because people, the human, are very, very complex creatures. So there's what we call here diversity of drivers. We have a bunch of people riding cars with different backgrounds, experience, teaching, different attitudes, different psychology. So no two drivers are the same. We have wildly varying characteristics of a driver. We have slow drivers, aggressive drivers, drunk drivers, speedy drivers. We have all kinds of drivers. We have very good drivers, we have very bad drivers, and so on. So we have to deal with them all, and we have to design our transportation system and traffic signal and traffic device to serve everyone, not only the best of the best. So that's our problem, to reduce the crashes that can happen and increase the safety level. So if we had, and this is what people are trying to do right now, if we have drivers that they act the same way, in other words, let's put all people in Teslas, where people will not control the cars as much as cars control people. So we have computers that control the cars, and in the future everybody's now going into the research of autonomous vehicles, where cars drive themselves. You just put your destination, sleep in the back, and you let the car do the job. If we have this in the future, then it's going to be easy, because we're dealing with computers. Computers do not have different psychology like people do. So in this case, traffic engineering safety will be amazing. It will be so easy for us to do. And then we have here human factors follow what we call here normal distribution. And in statistical part in this class, we're going to talk a bit about statistics, and normal distribution is one main part of that. Any factor that's random, and humans are random, follow this normal distribution, where most of the people fall in most around the middle. But we have extremes when you talk here about different human factors that are random. Any factors that are human is normal. When you talk about height, weight, and in traffic engineering, when you talk about reaction distance, reaction time, when we talk about speed, walking speed, when we talk about anything related to humans, most of the people are around the middle. But we have extremes, people who are very short, people who are very tall, people who have very slow reaction time, very big reaction time. When I say slow reaction time, they have long reaction time, or people who have very short reaction time, like athletes. So we have this kind of normal curve, and it's we have like it's infinite in the two sides, meaning that you can have really slow people on the side, or very high reaction people, like I said, a tennis player, for example, or a ping pong player, that he can have very fast reaction time. So human factors follow this normal distribution, like walking speed, driver reaction time. When we design the traffic engineering, we try to include everyone, but it's impossible to include everyone. Sometimes you cannot serve the extremes. For example, for the reaction time, well, this guy, he's a drunk, he has 8 seconds reaction time, so he's one of the extremes here. I cannot serve this guy to do my stopping side distance and design everything on the road for this guy. I try as much as I can to serve everyone, but sometimes it's going to be very expensive to serve everyone. So we use here something called the 85th percentile, which serves 85%, meaning that when I see here the reaction time is 3.5, meaning that, or the 85th percentile of your reaction time is 35, meaning that 85% of the people will be 3.5 seconds or less, which covers all that. Can we design it with a little bit more? Well, be my guest, try to do it. Sometimes you go up to 90%, meaning that we want to serve 90% of the population. But still, you will never be able to serve 100%. Why? Because people have infinite numbers on both sides. Sometimes you do the 15%, and this is case when we don't want to serve the really low numbers. When you talk here, but for example, about speeds, well, speed of pedestrians that we use in traffic signals, we use it 15%. Also, we serve 85% of the population, meaning that when I say here, for example, 3 feet per second is the 15 percentile of people, meaning that 85% of the people have this 3 or more, and this actually talks about speed. So sometimes you have very fast people, but they're slow people. For example, somebody on a kid, small kid, that he walks very, very slow. So in this case, we try to serve everyone, and if we have special conditions like a school or a senior house, then we try to get this number a little bit even lower than that. So this is what we call here this is a problem with using humans, that numbers are different. We do not have we have this diversity. You don't have everybody's the same. So here we use this 15 and 85 percentile. So here continue talking about percentile. So the percentile is a value and distribution for which the stated percentage of the population has a characteristic that is less than or equal than the specified value. So again, when I say here the percentile, when I say here the 85 percentile of walking speed is 16, meaning that 85% of the population have this 17 value or less. When I say here 3.5, for example, that's the 15 percentile. When I say here 15% percentile, meaning that under the area under this curve is always 100%. So we try to get rid of these sides here because they're extreme. So 1500 minus 15 is 85%. So 85% of the population have a value of 3.5 feet per second pedestrian speed or more. So where feasible, higher percentile characteristics can be employed. So sometimes we say, you know what, I have some money. Let's make sure that we serve also the people who are 2 feet per second. So here we try to stretch the limit a little bit and make your system to include as much as we can everyone. And again, we talked about these examples. 85% of the population have reaction 3.0 seconds or less. 15% of population have walking speed or 3 feet or second or less. So, or we can put it this way, 85% of population have walking speed of 3 feet per second or more. And this is how we use the 15 and 85 together. So again, this is called the normal curve, part of the statistical part, and it comes to the factors of people using the transportation system and how can we serve everyone if we put the people in this kind of curve, and any factor that's random, we put this into the curve. So diversity, well, any traffic system should accommodate all types of drivers and vehicles expected to use this facility. Sometimes we try to make sure that these extreme bad drivers are out of the system, so sometimes we can maintain this through some kind of licensing criteria. For example, people who have very bad eyesight, we give them limited license, or older people, we can give them only daytime license. And standards of vehicle design, sometimes we design the vehicle to help us with that as well. So another thing that we do here as traffic, so this is done by not engineers here, it's done by politicians and putting some rules. We help sometimes as traffic engineers, but this is what we do. We address this diversity by some kind of uniformity, and the best example of the word uniformity is to give the same message to drivers. If they drive here, if they drive to other cities around the whole states, we have the same message. A very good example is a traffic signal. Everybody in the world knows that red to stop, yellow to get ready to stop or will move, and green is to go. So that's what we call here uniformity, something that the message is given the same. Everybody knows that a stop sign looks like this and it's red, even if it's written in a different language. So here that's what you call here uniformity, the same message, so drivers won't be confused. So familiar and uniform look and function of roadway and traffic control device. We want to make it as uniform as possible. That's why we follow some of the manuals that help us to design the same signals, signs, markings in the same city, in the same area, so we don't get confused by, if you went to another city, they use a different system of signs, you get confused. That's very normal until we get used to it, but having this kind of confusion might cause crashes, and that's why we as traffic engineers, we use this uniformity. And uniformity is one thing that we want to make sure it is. We use the same messages throughout. So humans are very complex features. Our task as engineers is to find ways to provide drivers with information in a clear, effective, informative manner that includes safe and proper responses. And if you remember, guys, we talked about some of the things that are related to the user. We talked about visual acuity, we talked about perception reaction time. These are the things that we deal with when we design anything related to traffic and highway design. Also, another thing that we also tend to make sure that users are taken care of, but it's not a main thing, because some drivers have problem with hearing, some other psychology. So we have different hearings, personalities. Deaf drivers can still drive, so hearing is not a big thing that we make sure. Other drivers just put the radio on high, so they cannot hear anything. You cannot listen to horns. So we always make sure that visual, or what the driver can see, and also his reaction time, which these two are very related, because once you see something and you need to stop, you have your reaction time. So these two work together, and this is what we focus on as engineers, and we design our highway system, and also when we do traffic problem. When I say traffic, I'm talking mainly signs, signals, and markings. Also, sometimes psychology of the driver, the personality, could also be important. So, well, how can we force this? We don't do that. Again, it's by some kind of enforcement and licensing. So, for example, if you have an aggressive driver or a drunk driver who's caught by DI, we don't deal with that. The police and the law enforcement deals with that. Here, we're engineers. We try to design and manage traffic in a safe and a easy way. So we talk here about the eye. We have here the principal characteristics of the eye. We have different parts of the eye. Sometimes some kind of color, peripheral vision, static visual acuity, how can we see objects, some glare problems and how we solve this, and some depth perception. And how can we judge distances based on what you can see. When you see a deer, should we stop, and how can we see how far the deer is from us? And your textbook has a table of these different other visual factors that we use in traffic engineering, and we try to make sure that these are the things that we use to judge distance and color, so we can design our stuff that the drivers can see. That's the rest of the table. So there are lots related to the human eye, what we care about, and we have discussed this in a previous course, so I'm going to go very fast here. So there you have 3 cones of vision: the clear one where you can read, what you can see, and this is where you design, and also fairly clear vision where you can recognize color and stuff, and there you have peripheral vision. Peripheral vision is very important for us to estimate speed. So if you cover this peripheral vision and somebody moves behind you or next to you, you do not exactly know what's your speed and their speed. So this is an idea how fast you are and how fast people around you are. So it affects all our practice and functions. and we always want to design the signs to be within this 10-degree cone of both the fairly clear and accurate and clear, so you can read without moving the eye. You want the eye always to be in front of you. You can also make the letters and numbers as big as enough so you can definitely have the message as fast as possible. And also a very important thing as part is the color blinded. People notice that people do not know the difference between red and green, for example. So when we design new traffic signals, they add a little bit of yellow and blue to it, so drivers can recognize if they're color blinded the traffic signals. And definitely you always know that the red is on the top, the green is on the bottom. And if you're going to a city where the signals are horizontal, the red is on the left, the green is on the right. So we have this called uniformity of traffic signals. Also, the design of the colors of all the signs are also very well designed for the color blinded as well. Then we talked about the PIV. Again, we're repeating things that we did before, so I'm going to go very fast. PIV theory is the theory that tries to calculate the reaction time, any reaction you have, and we have lots of reactions, surprises in the driving task. So what's the driving task? It's simply a number of sensory cues, things that you need to react to. There's a truck, there's a car in front of me, I want to drive in the specific speed, I want to take the next exit. So it's a series of cues that motorists must monitor and respond to. And there is a deer, so what should I do? So should I take hit the brakes? Who's behind me? Have to look. So we have different cues, things that we need to do. And it goes to this PIV theory. Number one, you recognize that's a P, and then you have identified what cue you have, what's the problem you have, and you say, yeah, there's a problem, and then you make a decision. And finally, you make a decision, your head or your brain starts to make this order to your feet to hit the brakes. So this is the physical response. So these are the four parts that goes into your mind, which is P, perception, I, intellection or identification, E, emotion, V, volition or reaction. And these four gets into the number that we use in our design. We use it in transportation and highway class, and also use this a lot. We're going to use this a bit more in our design of traffic signals. That's why I'm repeating this. So the main thing, we've been using this a lot, I know that we have talked about this, is why is perception action time important? Because we define number one, your stopping distance and other distances that we use throughout our design. Do we need this in traffic engineering? Of course we do, because we're still working on the road, but we're going to do it in a different approach here. So we're going to determine the safe stopping side distance and minimum side distance. We use it to design traffic signs, the location of signs, and how do you put the markings. And we talk about side distance. We talk also about passing side distance, where we put the passing zones. So also all geometric design features, for example, horizontal curves, and this is the work done by the highway designers. It's not our work here, but we help with the signs and the markings. Well, if you remember this number, 2.5 seconds, and it's actually the 90th percentile of people. Here, we say when you say that, that's how it's defined. 90% of the population have 2.5 seconds or less. 2.5 seconds or less, and this is the number we used a lot in our transportation work. When we talk about a little bit more traffic engineering, when we want to define, and this is an example we'll be doing in class, when we want to design a traffic signal, the first thing we want to know is this guy in the middle, the yellow light. So when we design the yellow light here, we want to know how much time we need for this yellow light. It depends on your speed, the location, different other things. And we're going to design one of these on Wednesday. So they want to determine the length of the yellow phase at signalized intersection. And it's the 85th percentile, says that 1 second. So you can see it's not 2.5, it's just 1. Because when you're a traffic signal, you have a higher perception reaction time. So what does this mean? It says that 85% of the people at a traffic signal needs 1 second or less, 1 second or less to decide either they're gonna stop or move. Now 85% of the people need 1 second or less to either stop or go. And I'm going to talk about this yellow thing a lot in this class, where we have something called the dilemma zone. The dilemma zone is where you're a driver, should you stop or go? And we have different personalities here. We're going to design the yellow light, the time for that, based on this dilemma zone. So you might remember also this table. We did this also but this is kind of a wrap up of everything we do in highway and transportation, the different PRT for different situations. We talked about these two. If you're designing a traffic signal, the normal stop as a traffic signal, 1 second or less. 85% of people are 1 second or less. When you talk on a highway and want to stop, you put the 2.5 seconds or less. You use this when we put signs for an exit. And if you remember these different numbers we use in something called the decision side distance, I'm going to put the table also for that in a minute, where we have different, remember the A, B, C, D, E situations or scenarios, and each one has a different perception reaction time. And if you remember the two first one, just to stop on a highway or an urban road, so here the time goes up, and here when we what we call here the speed, path, direction changes in different situations, here we have more than complex situations. Let me give you an example. You want to get to the next exit and you find the sign that tells you the next exit is after 1 mile. So you want to put it in a specific way where if there is a truck next to you taking the right lane and you want to do different maneuvers. The first maneuver is to change to the other lane, maybe speed before the truck comes, and then change the lane so you can take the next exit. Put the signal and take this exit. So that's why the numbers here, the reaction time goes a little bit more, and this gives you what we call here decision side distance. We use this also to put signs, and it will tell you where to put the sign. Should put it after 1 mile, 2 miles, 1.5 mile, to tell you that there's a next exit that takes you to the city of Cincinnati or Columbus or wherever you want to go. Let's get back to the perception reaction time. Well, remember this equation here. You have the distance. When you can calculate now the distance, and this is the famous example we show non-engineers that how important is reaction time. And this also tells you when you put your eye away from the road for 5 seconds to read a message on your phone, how much distance you can get. We use this equation to make this magic. So the distance is equal to V times T, and if you want your distance in feet and you want to put your speed not in feet per second, you want to put it in miles per hour, then the distance here, let me put the equation, is equal 1.47. That's the change here. We change here from hour to second to get this in feet. So the 1.47 here is the conversion number times the speed in miles per hour. So we can put here in miles per hour. So 1.47 is changing this miles per hour to feet per second. So I can multiply this by the TR in seconds. So how do you how you get this 1.47? Well, we have how many feet in a mile divided by how many hours in a second. It will give me 1.46667, and this will be our conversion rate. Okay, we're going to solve some very simple questions about this in class, but I'm going to move ahead. This is an additional part here that they made an experiment about what we call here surprises or expectancy. We try to design our roads with least expectancy possible, meaning that when drivers expect something, they react faster. So we don't want to put some surprise or a driver not expected and then show them something. And that's why I keep saying a deer. Deer is something that you do not expect. You find the deer suddenly in front of the road. So this is an experiment shows that if we have alerted drivers, which are the squares here, and we have surprise drivers, you can notice here that the surprise driver has more reaction time than the alerted drivers. So this was an experiment and shows that we try to give as least surprises to the driver. So expectancy has significant impact on PRT. PRT, when I say here PRT, perception reaction time, drivers react more quickly to situations when they expect to encounter. Then we move to another people characteristics here. We talk about pedestrian, and we talk here about speed of pedestrians. Why do we use it? We use it for pedestrians crossing the roads. Why? Because you can, if you go here to fatal crashes, people who die when we have a car and a pedestrian, well, people are at a disadvantage here. 42% of people dying in crashes include pedestrians. When does this happen? When usually pedestrians cross the road either from intersection or from mid-block. And all other types of, you can see other types of crashes, pedestrians has 42% of crashes in 2011. So safety concerns for the vehicles, pedestrians are always in disadvantage. For it, so here we establish timing pattern for signalized intersections. When we design intersections, we want to figure out, we always have some kind of phase of pedestrians to cross the road, and we want to figure out what's their speed. So we also want to accommodate pedestrians as good as possible, because here we're losing lives. So we put here what we call here the walking speed, and again we use the normal curve because we have different speeds. I'm going to show you the table in a second, starting from a little kid up to an old person. So we have speeds. Most of the people are around the number in the middle, which is the 50th percentile. But when we design speed, we want to design a speed that's low as much as we can, so we can include everyone. So here we use the 15th percentile, which is about 3 to 3.5 feet per second, and it's always lower for areas with high number of seniors or schools. Okay guys, so and one new term here we'll be using a lot, especially when we design for signals, something called gap acceptance. Gap acceptance simply when you want to cross the road, and we don't have a signal. So when we want to cross, what we do is that we look at the cars, we find a gap. If we're accepted by this gap, it's I can cross while this gap is there. I go ahead and cross the road. So it's clear time intervals between vehicles encroaching the crossing path. So when you cross your path, you figure out how many cars are there, what's the gap between them. Some people say the gap is time, some other researchers say the gap is distance, and the behavior of pedestrians in accepting them so to cross through. So gap is measured as time lag between two vehicles, or the distance between the two vehicles. 85% by testing, they found that 85% of the people recognize 125 feet or more as my best gap acceptance, so I can cross the road. Okay, so and also we use this number and we use this gap acceptance. You don't have enough, we use it as a warrant. Warrant is something we use a lot in traffic. It's some kind of a red flag we give to the politician. Yeah, we want a signal there. The warrants are satisfied, so we put some kind of policies that would say, you know what, this sign has to be changed into a traffic signal. For example, where our school is, or any school is, if lots of students are crossing the road and there's crashes or there's problems or there's no gap acceptance, then this would be a warrant for us to install a push traffic signal to help students go from one side to another. And I have witnessed in Toronto, University of Toronto, between two buildings on the road, where they had these warrants, and we were able to install a push light traffic signal between these two buildings. Some of you might recognize this table, different years. It's a national study that shows the speeds of pedestrians. You can see here from 2.8 of a 2-year-old kid up to, let's say, 5.8 feet per second for a 12-year-old boy who runs. So here we have different numbers, so you can see these are the speeds. We try to use 3.5 or 3 feet per second, which is the 15 percentile of people will be served using this speed, so we can give enough time in the signal for these people to cross the road. There are other factors, the personality, the experience, motives, attitudes, some age, fatigue, alcohol and drugs, physical impairments, and some of these are being solved not by us but usually the law enforcement and police. Other factors which makes our job very hard, again, they are tried to be solved mainly by the police. Like we have elderly drivers, this is being solved by licensing issues, and road rage. We gotta get rid of the drivers who are aggressive and they make bad gestures on the road. We don't talk about road rage, aggressive drivers. These are the four out of the, it was actually a legal hearing in Washington DC about this. These are the different road rage characteristics of a driver that needs to be solved, and it's kind of a, you can say, a reaction to traffic congestion, how people react to that when they're stuck in traffic. So these are the 4 or 5 different points that road rage drivers or aggressive drivers tend to do. Then we talk now about vehicle characteristics. We have different vehicles on the road. How can we put these vehicles in a way that the road will serve all kinds of vehicles? And a good example is lane width. What's the best lane width that will include all these kinds of vehicles? So we need to figure out what are the different kinds of vehicles on the road. A very good example, you might see that when you drive on a toll road, is that the extreme right toll booth is kind of bigger than the other ones. And you might see on the road these huge cars that, it's for example a car holding a house, and I always wonder how this car passed the toll road. They usually go to the extreme right part of the toll road because this is the biggest part. So we have different kind of vehicles, and these are some of the characteristics that we consider: the length, width, height, wheelbase, weight, and also lots of things we use in highway design: acceleration, deceleration, equations we're going to talk about in a second, some speed and tire friction. These are used in our stopping side distance and passing side distance and other factors for the driver. And also we talk about the width. This is when we talk here about the width of a car. We talk also about the length when we use in turning. Height, when we have a clearance under a bridge, we want to know what's the clearance. The wheelbase is also used for when we have turning between at an intersection and between the first and the last axle, so we can have some kind of widening. The wheelbase is so an important thing. Weight also is an important thing when we deal with uphills and downhills, and we have different kinds of options for drivers, additional lanes, climbing lanes. So weight here is another problem or another issue. AAHSTO, which is the guy, you might have remembered this this manual from your highway design class, has 4 classes of vehicles, and this includes the passenger cars, buses, trucks, and RVs or different motor vehicles. And these are the 4 you can see here. These are the 4 different vehicle classes. From these 4 different classes, AAHSTO defined 20 what we call here design vehicles. When we do a design, we figure out what is the vehicle that we'll be mostly using, making sure that service vehicles, when I say service vehicles, the police, the fire trucks can go to this road. So usually a standard unit truck, the one used for garbage and mail delivery and also by the fire trucks, are probably the one that use in all local roads. So we have here 20 different vehicles, starting from passenger cars, and all these are kind of trucks, then buses, and all these WBs, and then the wheelbase length are different kinds of interstate 18-wheelers and trucks that are used. And then we have the motor houses. So we have here motor houses or car carrying a boat or motor house. We use these design vehicles when we simulate turning roadways, some curbs, lane width, and also lane widening on curves. What's the difference between these 3? Turning roadways, when we have a roadway that is turning, we want to know what is the length of this turning, what is the radius of this turning. When we have curbs, when we have an intersection and we want to make the turnings at intersection, we want to create these islands at the intersection. So we have here this triangular island. We want to know the radius of this turning curve. We want to know the regular lane width, and we have here between 10 to 12 feet. We also try to figure out what is the width of the biggest vehicle on the road. And also, when we do line widening, any turning, we don't keep the 12 or 11 feet, we go up to sometimes 20 feet. Why? I'm going to show you when we talk about simulation of this design vehicle. I think it's the next slide here. Yeah, so this is an example here for this. This is kind of a WB40 where we have a truck that's turning around. You can see this is the first axis and this is the last axis. Since they are in two different lines, when it turns, this is what we call here the lane widening. So this is not a regular lane width. We have widening because of this kind of problem. So when we have an exit at an interstate, when we have huge interstate trucks, trailers, and so on, so we figure out what is your turning radius out of this simulation. So these are the different turning radii for different design vehicles, and I have the 20 vehicles in two tables like you can see. So this is the radius and the minimum inside curb radius. We use this for highway design and also for traffic engineering work. The rest of the table, different kinds of WB trucks and the motor houses and the passenger car holding a boat or holding a trailer, holding a trailer, or a motor house with a boat. So that's the last one here. And then remember guys, this equation here, when we have fast turning moving cars, we use this equation here, R equals design speed squared divided by 15, E, which is the super elevation of the road, plus Fs. I'm not going to talk much about it, you're experts in that in transportation and highway design. And the only thing we want to make sure is that what is the value of Fs. Fs is the side friction that is activated once you do turning. So here the friction between the tires and the road holds the car when it's turning around, especially when we have a small radius. So this equation gives you the radius. So here these are different speeds, and every speed has a different side friction. The table below here is for wet conditions, so when we have water, and then the friction goes a little bit lower than we have in regular conditions. So this is the numbers that we use for wet conditions, and we use this to calculate the minimum radius of any turning highway. And also remember this, the braking distance, we use this in stopping side distance when we want to stop from one speed to another. This is when we want to stop from speed to 0, we want to do a complete stop, or you want to slow down. So the braking distance dB is equal to your speed squared divided by 30 plus the friction between the tires, and we can put the friction as this equation here, A over G, which A is the deceleration. Remember these two numbers, when we have a very fast deceleration 14.8 or a regular deceleration 11.2 divided by 32.2, which is the gravity. This gives me my F. G is the grade, so plus or minus, plus if you're going up, minus if you're going down. And if you're using two speeds where you, for example, have an exit and you want to slow down for this exit, so that's the first speed squared minus the second speed square. And based on these equations that we did today, we can now calculate the stopping side distance, which is the reaction distance, dr, 1.47 your speed times tr, reaction time. And then comes the second part, which is the braking distance, dB. Let's put the general equation. So it's u1 square minus u2 square. And if it's 0, it goes to the equation that you see. And this is, since we put u1 and u2, then here this is u1, your original speed. Divide by 30, A, which is the acceleration rate, divided by G, plus or minus the grade. Again, grade is uphill plus, minus downhill. Finally, guys, remember this table? We talked about the different kinds of decision side distance. And the decision side distance comes from the equations for the first two cases, A and B, this was to stop, if you remember, stop on a rural road, stop on an urban road. So the equation comes here, and we use now the maneuver time here, which is the time to stop. So that's how we do the first two, and then comes the last three. So here this is some kind of a change of path or distance, so we use this equation here, 1.47. We have 2 times the maneuver time and reaction time, which we had in the previous table, and you multiply here by your speed s. So this is the design speed here, so we have different design speed. So this gives you the decision side distance equations and decision side distance table. We use this also in our transportation class. I won't going to go much. Finally, guys, we're going to use this all these equations of stopping side distance, and we use the distance, and we use these reaction times to do something. And now I'm talking traffic engineering. I'm back to traffic engineering, and probably this is the only part we'll be grabbing or using from highway design. And now we're going to talk traffic engineering. We use all these equations to design something really important. We talked about this when we talked about the DZ, the dilemma zone. The dilemma zone is that when you're approaching the intersection, and then the signal was red, and then it starts turning yellow. Sorry, it was green. I'm sorry, it was green, and then it starts turning yellow before it turns red. How much yellow you need to give? So it's going to be based on 2 types of drivers. This driver here, where he will decide to stop. Is it safe for him to stop? We use the stopping side distance to define that. But what if this driver was here? We want this driver to safely approach the intersection, cross the intersection while yellow, and get away while yellow. So we're going to design 2 times. The first time is the yellow time. What is the yellow time? How can you get this yellow time? And number 2, something called AR time, all red time, where everybody's red. We don't give the other direction. It's green before we make sure that this guy was able to pass. Even when it turns red, we don't give green directly to this guy. We give some time to him to get away from the intersection. We're going to do this in an example. This way to approach this example is do an example. I'm going to do this in our class. I want to probably make a video just to solve this question, just to remind you how to do it. So we're going to solve as much questions as we can. By this, guys, I end the repetitive part of user, highway, and vehicle part of your design. And I wish you all a great week, and see you in class soon. Thank you, and have a great day.